Loud. So welcome everybody. Sorry for the relatively short notice of yesterday for this. Just my schedule is kind of tied up in the next few days. But hopefully this gets our studying started. We definitely, even if you haven't started studying, if you want to talk about this section, I think two things that might be good for us to focus on is some of the older stuff and some of the newer stuff. But I can definitely do other things as well. So in a moment, I will sort of ask you what questions you want. But in terms of material, I've mentioned that you should expect about 8 pages. This is typically the last two. Usually there's a couple pages, a little more emphasis on this stuff, I would say. That's pretty typical. The older stuff is usually 2 to 3 pages. This is usually around 1 to 2 pages. This is usually around 1 to 2 pages. So I would say the most common format is this um, in terms of structure. Um, yeah, so I'd have to look at that answer, but let's come back to that at the end. So the other thing I want to say, if you haven't checked it out yet, is on my on week 10 module. I do have these short videos I made last term. I don't know what's more helpful. These short videos, these longer videos. And then today I've been answering a lot of questions on the discussion board. I've tried to put titles so that you would know what other people have been asking. Um, and in doing that, I walked all the way through the 2024 final because there were quite a few questions on that. So I talked through the whole final. Um, and then I did a shorter version for the 2018 final. So I'm trying to give studying things in different forms that you can look at. All right, that's the agenda. Um, so what particular topics or are there any, if you have general questions, you can raise your hand and we can talk about them. If you have particular questions from old exams, you can blow up the chat now and I'll start to list them. And then my goal is to hit lots of different topics here. That's my plan. So any questions in the chat, particular old final questions, preferably from the last decade. So winter 23, 8C. So that's probably a Taylor series question. Winter 24, number 6. That must be something else. Space curves. How do we go to get a space curve? So given a position vector, how do you go about going to get a space curve? I think maybe you mean, Nathan, an intersection, like how to find winter 24 8C. Any Taylor questions? Thank you. I'm just getting kind of a collection of things. Centroid, center of mass. Yes, we can do something like that. And we may not do all these, but we'll kind of see something about space curves. I'm not quite understanding that question, but we'll hit it in a second. Applied or global max and min. So I would categorize those as applied, max and min, and then global max and min. So I think I'd like to start with something that has to do with Taylor series. So maybe we can hit a couple of these. Um, so let's go take a look at winter 23, space curves 2B. On which exam, Nathan? Oh, winter 23, 2B. So let's start with the winter 23 exam. And this is kind of like what I did in the last exam. We'll tour through it, but we'll make sure to hit those points. Um, winter 23. Oh, and I think maybe I posted a video already where I toured some of these first questions. Um, I did post that earlier today. I can't keep track. I posted something where I said a few small words about these earlier questions. Um, 2B. Ah, this is the one. Um, that contains the space curve. Yes. So let's address this quickly and then we'll go to the Taylor series here. Um, oh, I didn't actually do the whole question. I just said a general thing. Okay, so let's do the first part of this question. This is Winter 23 2, and then we'll talk about part B. I think we can do this one fairly quickly, but it hits a few key points, and then we'll move on to the other question at the end. So what they're telling you is that these are the derivatives, and they tell you this is the initial condition. And so this question is about integrating. We have basically have three problems to do. We need to integrate this. We also need to integrate this. We also need to integrate this. And they gave us three initial conditions. So anyways, this one's going to be 3 sine of t plus a constant. I'm going to call it C1. This one's going to be 2t squared plus C2. This one's going to be negative cosine of t plus C3. So that's our position function. And we were given an initial condition that when we plug in 0, we're supposed to get 2, 1, -1. So you actually have to plug it in, but in this case, when you plug in 0, you get 3 times 0. So you get 0 plus C1 has to be 2. So C2 has to be 2. Or C1 has to be 2. You get 0 plus C2 is 1. I'm getting that all from here. And when you plug in a 0 here, you get -1 plus C3 has to be -1. So C3 is 0. Okay, so let's just assess and make sure we're in the same place, and then we'll answer part B. 2c squared negative cosine of t. Oh, this is 1 plus 1. And the first one was 2. I can't seem to copy. Plus 2, 2t squared plus 1, and negative cosine of t. Ah, I got it now. So I think when I flipped through this exam earlier today, I didn't see that. Are we good on part A? Give me a thumbs up or something. Part A is okay. Good, good. All right. So part B, so these notes I have down here are not correct. Let me get rid of this piece. Okay, so part B said, can you give an equation? Find the equation of a surface that contains the space curve. So what that's saying is, assume you know that x is 3 sine of t plus 2, and that y is 2t squared plus 1, and that z is negative cosine of t from the previous part. And this question is really about visualizing. So how could we visualize this? Is there a surface that it lives on, so to speak? So back when we did this, this was called, we said it a few different ways. We're eliminating the parameter, and there's actually many correct answers. There's one that to me would be the best for visualizing. But one correct answer would be just to solve for t and substitute it into the others. So what this is asking you to do is, can you get rid of t and find the surface you're on? As a quick visual, this is not the same problem, but here's an example of a cylinder intersecting with a plane. That's an example we like. So if you wanted to describe the curve that's on this intersection, you could say, well, it's on the cylinder. It's also on the plane. And it also might be on something else. So that's what this question is saying. Which surfaces is this curve on? It's not maybe a cylinder or a plane. What can we say? Okay, so one option is to solve for t. That's probably going to be a mess. The two options are this. Solve for t and then shove that into one of the other equations. That's sort of option one. And you can do that here. It's kind of messy because you get y minus 1 is 2t squared. So you would get t squared is y minus 1 over 2. And you would get t as plus or minus the square root of y minus 1 over 2. and then shove that in one of the other ones. So you could say z equals negative cosine plus or minus the square root of y minus 1 over 2, and I would accept that. That would get full credit. That is one surface, actually a cylinder, we would say a cosine cylinder. That's not the nicest of them. There's one that's nicer. So strategy one is to solve for t and shove it in the others and find a surface of motion. There's a second strategy, and the second strategy for eliminating the parameter was if there's sine and cosine, use the fact that cosine of theta squared plus sine of theta squared is always 1. So those are our two strategies. In this case, I do see sine and cosine. They're right here. So there is circular motion happening. But in order to use this fact, you have to get the sine and cosine by themselves. So let's do that now. So this is saying that sine of t, let's see if we can rearrange it, is x minus 2 divided by 3. This one is saying that cosine of t is negative z. Now we can put them together and say the first one squared plus the second one squared has to be 1. So x minus 2 over 3 squared plus negative z squared has to be 1. And that's an ellipse. So this motion is happening on an ellipse. It's also happening on whatever in the world this is. And if we had time, I'd pull up a 3D visual and show you this curve is on the intersection of several surfaces. But that's what the question was asking you to do, was to eliminate the parameter so that to help you visualize. That's why we do that. Does that make sense, Nathan? Yeah, wonderful. So we did that. I'm going to keep moving through this exam. Curvature is a straight computation thing. Have that formula ready. Find the global max and min. But the question somebody was
The
asking was,
curvature equation is r prime crossed with r double prime over.
yes, thank you, Jacob. That sounded like Jacob. R prime cross R double prime. Lovely. Over R prime of t cubed. And the comment, one comment about this is you're plugging in pi. And when you do a problem like this, it, the final is less of an issue, but computation time is much better if you plug in pi earlier in the problem. What I mean is they already told you R prime, it's here. I'd compute R double prime. Oh, no problem, Jacob. Well, was it Jacob or somebody else? Oh, no, it doesn't say Jacob. It says iPad, but it was helpful. The equations we find are surfaces that the motion is happening on. So if I had a bug, going around the rim of this cup, the cup would be a surface the bug is on. Um, so it's not, I guess, yeah, it's not quite the same as a trace. Here we're using the surface to help us visualize the curve. I think I have one thing I should say here before eventually this will get more organized, but if you go to this channel, I've been trying to make lots of stuff like this, but if you wanted surface of motion, you probably could find it. My channel's getting big enough. Yeah, so right here, surface of motion. Here's where we did this in 13.1, visualizing curves, and you can see cool visuals there, or I think they're cool, of how we, starting with a curve, how does knowing a surface is on help us visualize? That's part of why I'm making these, so that when people have bigger questions, I have something to point them to. But yeah, go to my channel and do a search. Eventually, I'll clean it up, but this is the beginning of me doing that. Okay, so then we have global min and max. The question was about, I did this question on the discussion board. There's a volume question. The question was about question 8. So sorry I'm taking so long. This is to reverse the order. Question 8C. Lovely. Okay, so this hits several people were asking questions of this sort. So this was winter 2023. question 8 on Taylor series. Now we don't, most quarters we don't provide this. They must have decided that quarter as a group to provide this. So I would put those on your note sheet. You don't have a guarantee those are going to be on there. But this question is use those to get this Taylor series. The question's about part C, but I want to do the first part too. So sorry, we're going to do that. So what I
It's
see
fine
is
by me.
one of them looks kind of like this,
Balance.
and one of
People
them
were here before.
contains this a little bit. And somebody, participants. Mute all current new. Okay. Sorry. So let's go now. So now we're going to do some rearranging. So the first one has an x cubed on top. We're just going to factor it out. So x cubed times 1 over 1 plus x to the fourth. Sometimes people have questions about that, but you can do that with fractions. 3 halves is the same as 3 times a half. Okay, so assuming we have that. The other thing is it doesn't quite look right, so we use our typical little trick here, which is to write 1 minus, and then we write minus x to the fourth. That's it. That's the maneuvering we do so that we can just shove the thing directly in here. So now we're going to replace this x and this x with negative x to the fourth. So let's do that sort of carefully. X to the third is still there out in front. You have the sum from k equals 0 to infinity, and we have this to the k. Now, the more of this we can do kind of in line, the less writing we have to do. So normally I would not write what I'm doing now. I would have already simplified it. So that's the Taylor series for this. How are we doing there? So all we really did, if you want to break it down, is we just shoved it in there. This we can simplify. You can leave the x cubed on the outside. I'm going to say something about it in a second. So now I'm going to switch to writing it in a more user-friendly form. It doesn't really matter for this part. Like I would accept that for this part, but I suspect in part C, we are going to need to have this more simplified. So just, I haven't even looked at part C yet, but I suspect we will. So I'm going to do it here. I'm going to write x cubed. I'm going to write the sum from k equals 0 to infinity. And I'm going to write negative 1 to the k, x to the 4k. So that's me simplifying that. And that's because it was negative 1 times x to the fourth all to the k. And it's much better to do it in that form because it separates the numbers in the x. If you want to move the x to the third inside, you can, and you can even do better than that. X to the 4k times x to the third is x to the 4k plus 3. So this is the sum from k equals 0 to infinity, negative 1 to the k, x to the 4k plus 3. So that's probably as clean as it can get. Like I said, you don't have to go past here to get this part correct, but that was cleaning up. And all that really happened was that we put negative x to the fourth in here. Okay, so that's the first one. But I am keeping track of what we put in there. So we put that in there. Great. Now we're going to do the other one, the 3x sine of x squared. The thing that we have that looks similar is sine. And so let's do this. We're going to have 3x times sine of x squared. So I guess be ready. I'll try to think of something I can ask you to do in the chat. So we're going to replace this x with x squared. So maybe what I'll ask you in the chat is what will the exponent become? So if you do x squared to the 2k plus 1, that is x to the what? So tell me in the chat what that is. Looks like we're getting it. So I'm going to write equals 3x. I'm going to write the sum from k equals 0 to infinity, -1 to the k, 2k plus 1 factorial, and then I'm putting an x squared in. So based off of what everyone's saying in the chat, it's going to be x to the 4k plus 2. And we've done it, but let's just for fun move the 3 and the x in there. So like at this point we are done with that one too, but let's practice moving it. So I'm going to have the sum from k equals 0 to infinity, 3 times -1 to the k over 2k plus 1 factorial x to the 4k plus 3. So there's the Taylor series for that one in all its glory. The way the question is asked, it doesn't say I have to put them together. So the final answer is this minus this. They happen to match up, meaning whoever wrote this question made sure that the powers lined up in a nice way. And then the indices line up. So if you want to write it in one huge monster of an answer, you can. And it would be this big monster x to the 4k plus 3. And then I need to do the first one minus the second one. So -1 to the k. Oh, the first one's not that bad. It's just -1 to the k. The second one is plus, not plus, I'm subtracting. Right here. So minus, and then I'm going to write 3. And that's it. I guess I didn't need as much space as I thought. So this was really two separate questions. Question 1 was this. Question 2 was this. And we're just learning this, so it makes sense. We're having to kind of learn this right now. And the putting them together is fine. On some of the homework questions, they want us to do k equals 1. That's just one homework question. That's that question 2. It's very particular to that question. So I do want, is this it? Is this my current? Yeah. So I do want you to check out this post where I talk about this. It just so happens in that homework question that the k equals 0 term cancels. That's why they can ask it that way. It's really unique to that problem. So check that post. I'm going to always use k equals 0. There are some, like if you look online, you can index it. You could start at k equals -5,000, but it's a pattern forming thing. Maybe we can talk about that in a second. But I want to get to the part of the question that was asked. Okay, open interval convergence goes back to what we plugged in. So we plugged into the sine series, which works for all values, and we plugged into the geometric series, which works for values here. So before we move on, let's think about what we plugged in. So the thing that we plugged into the geometric series was -x to the 4th. And the thing that we plugged into the sine series was x squared. So I am only allowed to have numbers that satisfy both of those. So that's what this is asking. Now, everything would work here. There's kind of an interesting question here. Somebody asked me after class, how do I simplify that? And there's kind of if you just want one general answer, you just try to solve both of these and then make appropriate conclusions on your number line. One of those things can actually never happen. You can never have x to the fourth equals -1. But x to the fourth equals 1 actually has two answers. X equals plus or minus 1. But so if you use that approach, you say, well, there's the only way I can be equal to the end is plus or minus 1. And then you try numbers. You know, the numbers between -1 and 1 work here. So it turns out to just be -1 to 1. But mostly this is about keeping track of what you plugged in and where you plugged it in. Okay, so the actual question being asked is a pattern finding question. So this isn't, we'll do something like this in class tomorrow, but this is a one way to ask about the pattern that we just found. So this is asking you to read information off of this. And so I'm going to explain that now. I'm glad you asked this. Okay. So how do we read a pattern off? There's two ways we read the pattern off. One is we ask for the first few terms. And that would just mean plug in k equals 0, k equals 1, k equals 2, and stop. That's often a way. So be ready for that sort of question on the test. Another way is we could ask you about a particular term, which is what this is doing. So this question is actually asking you the following. What happens when you get to the x to the 2023? What is sitting in front of it? So the moment you see this, that's what we should be thinking. I'll explain why in a second. But now I'm going to go up here and I'm going to ask myself, does this ever make it to 2023? And when it does, what can I say about the stuff that's in front of it? Maybe let's do that question first. So my question right now, before we answer the actual question, is when is this exponent going to be 2023? And at that moment, what's all this stuff in front of it? So in the chat, can you tell me what k is? So k is not 2023. So 4k plus 3 is, oh, is it 5? It's a nice number. Nice-ish. 505. Ah, yeah. So 4k is 2020. Half of that is 1010. Half of that is 505. So you're saying 505. So the moment you see this question, just go, I need the exponent to be this. Okay, so now we're going to fill in the rest. What happens if I replace all of these k's by 505? Let's do that now. So I'm going to have -1 to the 505, which is just -1. And I'm going to have -3, -1 to the 505. And then on the bottom, I'm going to have 2k plus 1. So I'm going to compute that now. 2 times 505 plus 1 is 1011, I think. So I'm going to have 1011 factorial. Okay, I think that's what it will look like. So when you get to the power 2023, that's what it'll look like. And we could even simplify it a little more because it's going to be -1. This is going to be negative, so then it's going to be plus 3 over 111 factorial. So the two types of ways we ask you to use the series are give the first few terms or give me a particular term way down the road. And that's what you'll do when you see that. Now I need to explain how that ties in with what was actually being asked. But are we okay so far? So the x, whatever the power is, that's what we're doing. So how does this tie in with the derivative? And it's not asking you to take 2023 derivatives. The reason they're picking such a big number is to try to discourage someone even attempting taking the derivatives. Okay, so here's how this ties in. When we started this whole process, we said the following. We said the Taylor series has the following pattern. X squared dot dot dot. When you get to like the 10th term, there's going to be a 10 factorial. There's going to be a 10th derivative. And you're going to have x to the 10th. And that's going to keep going. And that should give us the same thing as the pattern we just found. So if you keep going for a long, long time, you're eventually going to get to 2023. And what should be in front of it if we'd used the derivative method? Well, in front of it would have been the 2023rd derivative at 0. And we would have had to divide by what? So forget what we've done so far. I'm separating this. If we had done this the extremely long way and actually taken 2023 derivatives, what would be sitting right in front of it here? So when it's the 10th derivative, we have 10 factorial, 1 over 10 factorial in front of it. If it's the second derivative, so it's going to be 2023 factorial. Okay, so what this question is asking is you to put these two ideas together. It says, this is what it should be if we'd have done the derivative method. This is what we got from the shortcut method. So these two things are the same. So if you want to process for an exam, here's what you do. You find when the exponent matches that. You find the number in front of x. And then your very last step in the problem is to think of it this way. 2023 factorial, 2023 of 0 is the same as this thing. Which means we get this weird indirect fact that the 2023 derivative equals this thing times 2023 factorial. I think only once ever have I seen an application of this, and I can't even remember what it was in graduate school, where you are using the Taylor series to find derivatives. So this is just a goofy pattern question. So this would be our final answer. But I would categorize this as a pattern question. So yes, we can do the sigma notation. Here's where the sigma notation is valuable if we'd like to know something way down the road. It's not gone. These two things, good question. Somebody's asking, where did the 2023 go? I decided not to write it. You could put it there, but this thing is the same as, need a better color, this thing. So that is the same as this. But I just canceled the 2023s. I'm just trying to, that means the number in front of this is the same as the number in front of this. You with me there? So I could have put the 2023 here and the 2023 here and then said, oh, we can cancel those, if that helps. So the two types of pattern questions are to write out the first few terms or to give me a particular term way down the road. Well, we think about that for a second. I took a little time there, but I think I'm gonna go to my review page. And oh, it's all squished up because I'm zoomed way in. I think this test prep from last Thursday, I tried to hit, so now it might be a good time to revisit. I tried to do each type of pattern question. So here you can see a pattern question with the derivative. Here's a pattern question that says find the third Taylor polynomial. Here's the 2017th derivative. Here's the 100th derivative. So there's a bunch in here. And I have real detailed solutions. So let's look at some since we just were talking about this. So I actually wrote them up on pencil and paper. It's a couple years older. But you can see what I did. So when it asked me for the 10th derivative, I found when the exponent was 10, and then I multiplied both sides by 10 factorial. When it asked me for, let's look at another one, the 2017th derivative, I found when the exponent was 2017. Okay, so once we've seen a couple of these, but the point of that is, if you really want to be ready, I tried to make these two test preps Very good preparation for the exam. So if you want to be completely ready for error bounds, this will take care of you. If you want to be completely ready for Taylor series, this will take care of you. Has all the main things you would deal with. All right. That was the point of that test prep. Other questions there? No, it's a bit to take in, but I feel like we did Taylor series and we found the 2023rd derivative. And then we did this one, which I've now forgotten. No, I remember. It's a surface of motion. This is this one, surface of motion. And sorry, we didn't get through that much there on those couple, but I think we were hopefully hitting some quality things. So I'm going to move, we can do more Taylor series stuff, but I'm going to move to just go down the list. Question 6 will probably be something else. Maybe it'll give us a break. Then we could circle back. I don't know if this was winter 2022. I unfortunately erased it and bumped it. Okay, so let's look at winter 2024. And there's a question about number 6, but we'll do a tour while we're going. Ooh, so do we have a plan of attack for finding a line of intersection? So I like to always, if I was preparing for an exam, I like to sort of go, would I know? Yeah, we're going to combine. Ultimately, we're looking for x equals something plus something times t, y equals something plus something times t, z equals, and we're looking for a point and a direction. If you caught my perspective on this, I always feel like if I have to find one point, I might as well find two, and if I can find 2 points, I'm done. But because there are 3 equations, it would be better to combine. Probably the easiest way to combine is to add them side by side, simply because I can see these are going to cancel. But you can also simplify in other ways. Solve for a variable, shove it in. Whatever you do after you combine, there should be fewer variables. And then we would find 2 points and we would be done. So if you do A minus B or B minus A, that can go here. But this was one of those problems where we got to pick our points. All right, I spent too much time. The question was on number 6. Find the intersection point of the line with this plane. Okay, that's not too bad. Okay. And there was another strategy for this one, but I'm going to leave it. So let's keep going. Consider the curve given by this. Find the curvature. So we'd have that formula. Find the point where the tangent line is orthogonal to this. Ooh, we can come back and talk about that. Tangent line. Angle of intersection. All right, I remember that. Find all the saddle points. So finding the critical points. Absolute max and min. Ooh, this looks like our midterm exam question. We're trying to get the point that's closest to this point. So hopefully now after the midterm, we would have an immediate plan. X squared plus y minus 3. We're trying to minimize this. And so the given information we're going to use to get rid of one of these variables and make this a 2-variable function. At first glance, to me, it looks like the x squared would actually be the easiest because you have x squared is 2 plus y plus 1 squared. And that looks like that would be nice to substitute right here. Partial derivative, set them equal to 0, and you're in business. But the question was about 6. I'll get there eventually. I think this is valuable for us to kind of peek through lots of questions as we guide towards other things. We have order of integration, evaluation, and then this question. Oh, all right. This question has a soft spot in my heart here. I'll explain why at the end. Was this the question somebody's asking? Did someone want to look at this one? Yes, thank you, Lily. Find the volume of the region that's inside the ellipsoid and above the cone. This is similar to a homework question, um, but it's a volume question. So we have visualizing will help, possibly, but we have a routine. So I've given a routine of things you can do when you're stuck. And that routine is find the Z's, draw the region. And I had two things to be doing to help you draw the region. And that was, what are your given XY equations? And then do the Z's intersect? So this is kind of our automatic things we do. So there are two Z's in this problem. There's this Z and there's this Z. And I sure would like that Z to be by itself. So my immediate reaction would be to do this. Do it carefully. I did see some students mess that part up on the test, the solving here. And then I'm going to divide everything by 4. And then I'm going to do the square root. Now, we may have to think in a moment about, and I did see some students distribute the square root. That's called the sophomore's dream. And unfortunately, it's not true. You can't distribute square roots as much as we would like to. But this is not the same as this. I didn't come up with the sophomore's dream. That statement has been around for years. Those are not the same. You can't distribute, you're stuck. Okay, so we may have a bit to interpret, but I know immediately that I'm doing volumes under this surface. And I know I'm also doing volumes under this surface. That darn 4. I guess it would have been better if I'd have factored out the 4. Oh well. All right, 1/4 y squared dA. So I have 2 volumes to do, so that means I have some work ahead of me. But I'm going to worry about that in a second. Okay, so I'll worry about interpreting. Next step, let's draw the given region on the ground. So double integrals always have a region on the ground and a surface. In this case, we have 2 surfaces. Okay, are there any given XY equations? No, darn it. So we're down to one thing to do, which is do the surfaces intersect? They must, or the question doesn't make any sense. If there are no given bounds and the surfaces don't intersect, then there is no volume between them because they just go on forever. Do those two things intersect? And I would like to get an XY equation. So that's when we substitute in. So that's this step here. Here we really need that step. So I'm going to substitute for this Z squared. I'm going to substitute in this Z. So I get plus 4. And since it's the square root squared, I get x squared plus y squared is 25. And now we're going to simplify that. So I think that gives me 5 x squared plus y squared is 25. And we get x squared plus y squared is 5. And that's a circle of radius square root of 5. So those are things, even in a complicated problem, we can do automatically. Any questions so far? So find your z's, draw your region. You can definitely do polar. Polar is what you should do. You could do it other ways, but polar is the best way. So then we do polar, we calculate each one, we subtract. A very common question I'm getting is, how do I know which one of these is bigger? You don't even have to know. You could wait till the end, but if you wanted to know, just pick a random point in the middle. You could also, the description also tells me, like, well, 0, 0. Plug in 0, 0 here, plug in 0, 0 here, and see which one's bigger. I don't, yeah, so when I set it up, I worry about this at the end. So I will worry about interpreting at the end, whether it should be a plus or minus or what we're going to do. Um, but the problem also tells me, so here's where the point of me saying this is it would help to visualize a little bit, but I wanted to show you you could do all of that without visualizing. Now, when they said ellipsoid, in my head, I was thinking, okay, we got some sort of squished sphere. When they said it was inside the ellipsoid, which is what it says here, that gave me a little information. And then when they said it was above this cone, this is the positive cone, it looks like this. In my head, I was like, okay, I don't have to worry about the negative. Why not? Because we're not even talking about the lower hemisphere. We're talking about this volume up here. So that's where it helped me. I knew already from the beginning that I didn't have to worry about the lower hemisphere because the question says it's above the cone and below the ellipsoid. But that often confuses people. So that's why I wanted to show you you can really do essentially everything. Now the bounds here are theta is 0 to 2 pi. R is 0 to root 5. And here there's not really an advantage to putting them together. So I would have 0 to 2 pi, 0 to root 5. This would be R. So R, dr. Oh, I'm wrong. This is R. And then the dA is R, dr, d theta. I was too excited to speak like a pirate. Tried to skip it. And then the other one would be 0 to 2 pi, 0 to root 5. And then this, there's an R squared there. So it's negative 1/4 x squared plus y squared. So it's the square root of 25 over 4 minus 1/4 r squared, r dr d theta. And I would just compute those separately. Now, the first one I think is pretty nice to compute. The second one's going to require a substitution. So I have to pause and say something here at the end of this question. But so this was the bounds, step 3. And then step 4 would be compute. At the end of it, you would have 2 volumes and then do the bigger one minus the smaller one, and that's your answer. Questions on that setup before I show you something related to this problem? And we'll be right back, but is there a good non-geometric way to know we don't need to do the plus or minus? If we're ever unsure, you could just go all the way to the bitter end, meaning if you take a picture of where this comes into play, even if I included the plus or minus, all the integration would be the same. You just at the very end would have this plus or minus. And so in the last moment of the question, you could wait till the very last line to interpret, is the point I want to make. There is some credit for interpreting correctly. And that will require you think about the fact that, is this a plus or minus? Oh, and you'd have to go back and say it's inside the ellipsoid and above the cone. So there's no way around that, but we can make it to the very last moment of the question before we have to consider that even. But I think I'm going to do this. I'm going to pull up this and show you something here. So one of my students, would we not do the ellipsoid cone since the cone's on top? The cone's not on top. Let me show you. This will answer your question, I think. Somebody's asked me a private question. One of my calculus students from 2 quarters ago that's now in engineering, this question kind of bugged him. And so he joined a group of students that made some visuals. And he made a 3D print of this problem. This is this exact problem you're asking me. That's why I said that. Oh, this is the wrong person. I need to change the name. This is somebody else. Um, anyways, and he made the world's best video on this. There's no speaking. But if you want a good explanation, you should just watch this. So he made some visuals using this Manim software. That's the volume we're finding between that ellipsoid and that cone. We're trying to find the volume. He made like a 3-minute video where he completely explained it. He put a bunch of work into this. So if you want to watch this, he says, here's how you do it. He does it with the equations. His videos are way better than mine. That's what we just did, but he did it in a much prettier way. And then we are finding the volume above that circle. So that circle he's highlighting there, imagine it's on the ground. You can ignore what it says there about cylindrical, but and we're finding the volume between them. That's part of our goal, is to make things like this that hopefully remove some confusion. He put the two integrals together, the volume under the ellipsoid and under the cone. So I hope to do more of that in the years to come, but I did not make that one. Uh-oh, we're going to get the answer here. I guess it doesn't matter. It's an exam question. Spectacular. All right. So you can come to our presentation on Thursday at 5:30 in Denny 303, and you can thank that student directly. All right, that's in our gallery of stuff. Yeah, this is on the website. It's new. This is the gallery of calculus visuals. We made 3D prints of all these, which are several, some from this course. I made the animations, but he made that animation. And then there's some other weird stuff we threw in. All right. Sorry, that was a distraction. You just asked the exact question that the student asked. Anyways, this is this. So we did a applied volume, I would say. So let's look at something else. Who asked this third question? Was it also a winter 2023? I apologize because I scribbled when I came back and I couldn't remember if it was 23 or 24. Or was it the same question? 24. It was 24. 24, number 8C. Let's kind of circle back. Winter 24. Oh, we were already on it. Find the second Taylor polynomial. That's not what the question was, but you're going to take derivatives. Derivatives, derivatives, derivatives. And then we're going to do this. So let's play this game. All right, let's circle back to a Taylor polynomial, Taylor series question. I'm going to go till 6 or shortly after. I have a kids' baseball game at 7. And he'll be mad at me if I'm on too much to get too close to that. But after 6 should be fine. All right. So here we go. Let's play this game again because we did this at the beginning. I'm substituting. In fact, this is very similar to the one we already did. Maybe it'd be better if we had something more exciting here. But I'm going to replace the x in the sine series with x to the 4th. So in fact, let me do it this way. Sine, try to write it a different way, equals, I'm going to leave some space, the sum, -1 to the k, 2k plus 1 factorial, blah, to the 2k plus 1. So that's the known pattern. The second one's gonna require a little bit of finesse, but let's do the first one. So the first one says, what I have is an x right here, and I have an x to the 4th here. So I'm going to put an x to the 4th here. I'm going to put an x here. Done. Now that's the Taylor series. The question actually asked me for the 10th Taylor polynomial, but I'll deal with that at the end. So right now I've got the pattern. Let's play the simplifying the pattern game. So this is x times the sum from k equals 0 to infinity, negative 1 to the k, 2k plus 1 factorial, x to the 8k plus 4. And just to see, I probably have put everyone to sleep a long time ago, but if you distribute this x, what will my exponent be after I distribute the x? You can blow up the chat. So I've been talking for too long. Oh, somebody's awake. Thank you. All right. So sounds like many of you are awake. I was completely wrong. Okay, k, 2k plus 1 factorial x to the 8k plus 5. So all I was doing there was kind of house cleaning, putting it in a more user-friendly form. This was the answer for the pattern. All right, now let's play the game for this one. So really these are just like two separate questions together. I'll worry about the 10th Taylor polynomial piece to finish this, but I want to separate our challenges. Okay, what bothers me about this one is that 4. The x squared also bothers me, so let's yank those out. So I'm going to come down here and I'm going to write, choose my red, x squared over 4. And then I'm going to write times, so that gives me the 1 on top. That gives me the 1 here. But now the challenge. So if I factor this 4 out of the denominator, it's like I've divided both these things by 4. So this is going to be 1/4 x to the third. In fact, I should have used my blue. Oh, blue would have been better. 1/4 x to the third. Oh, and there is something kind of interesting here after we go a little bit further. So now I'm going to use the Taylor series here. The geometric series. The geometric series has the nicest pattern because it's just 1 that's in front of it and then blank to the k. And I'm putting this here. And if we play the house cleaning game here, this is going to be, so we're done. That's the Taylor series for this. But let's make it look prettier. So it's going to be x squared over 4, the sum from k equals 0 to infinity, 1 over 4 to the k, x to the 3k. I think a textbook would always take an extra step here. They'd put the x squared inside, which is going to add 2 to the exponent. They'd put the 1/4 inside, which adds 1 to that exponent. This is not necessary at all, but I'm going to do it anyways. X to the 3k plus 2. So we've done it. That's probably the cleanest way you can state the pattern for the Taylor series for the first one, and probably the cleanest way you can state the pattern for the second one. The question did not ask for the general pattern, so I did more than was necessary. The question asked for the 10th Taylor polynomial. So I'm glad this came up because this reminds me I need to say something tomorrow about this, but this means we're going to go up to x to the 4th and no further. So I would like to extract everything from these up to x to the 4th. That might seem like a lot of work, so let's maybe just practice how do we extract the first and second and third terms. And then I need to add them together. So let's look at this first one. If I plug in, let's do a little bit of evaluation practice. Go ahead and put a 0 in everywhere. It's nice if you can simplify as you go, but I'm just going to blindly put it in. X to the 8 times 0 plus 5. That simplifies a lot. It's just 1 over 1 x to the 5th. So that is just x to the 5th. So if I was doing it myself, I wouldn't have written all that out, but I just wanted to show that I just plugged in the 0 to all of these spots. If you plug in 1, what happens? The next thing we would get is x to the 8 plus 5. What's 8 plus 5 if you're still awake? Why is it not? It's 13. Yeah, so the next one is 13. But there was a question that popped up right before we blew up the chat. I'm gonna go find it. Oh, I think Jacob. Jacob, why is it 2x to the fourth, not x to the 10th? Oh, I gotcha. I was like, what is he talking about? It's because I wrote the wrong thing. Everything up to x to the 10th. I don't know why I wrote 4. Did I say 4? Thank you, Jacob, for pointing that out. Holy cow. It's everything up to that power. Whew. I'm glad you caught that. So, anyways, the point here is we don't even need to go any further because the next one's going to be 13, and that's too big. Okay, so from the first one, all I get is x to the fifth. And then everything else is going to be a bigger power. So now we're going to move to the second one. So if you only go up to x to the... In fact, if you knew your Taylor series really well, we might even be able to see that from the get-go, but that's not the goal. So this is approximately x to the fifth plus... We might even say it this way. Here's a bit of fancy math speak. This is approximately equal to x in the fifth plus something of order x to the 13th. Now, you don't need to know this at all. Pretend I didn't say this. But the next term has order 13th or bigger. And since they only wanted all the stuff up to order 10, we don't need to go any further. Okay, so that's one way to think of it. That's what we would say, this big O notation. Okay, so the next thing is what can we say about this? So now we're going to plug in a 0. It's going to be 1 over 4x to the 2. And then we're going to plug in a 1. 1 over 4 squared x. So if I plug in a 1 here, I get 3 plus 2, which is 5. And then I'm going to go another 1. 1 over 4 cubed x to the... Now I'm going to plug in a 2. 2 times 3 is 6, plus 2 is 8. The next one is going to be 1 over 4 to the fourth, x to the, and if I plug in a 3, I get 11. When do I stop? You don't go to 11. So your final answer would be this plus this. So that's probably one of the more convoluted final answers. And we could put these two together and call you could leave them apart or put them together. I guess that's 1/16, so 17/16. So I bet the solution says, somebody can let me know if the solutions say this. Do they say 17/16 x to the fifth plus 1 over 4 times 4 is 16 times 4 is 64? Is this what it says in the solutions? Winter 2024? Or they may have the full solutions, I don't know. But the main thing was the pattern. So I wanted to go back. This is what you actually need to do the problem. Then it was saying, can you use that pattern to give the first few terms? And as I always like to say, if the sigma notation is causing us trouble, just do it again without the sigma notation. It takes longer. But this meant everything up to the 10th power. Is that okay? The question was about part C, but great. Stephanie, go ahead.
I just had a question. So like whenever like it says like t to like the like if it wants like the 10th polynomial, will it always end in like x to the 10th? Like for example, if we were saying like, oh, find the fourth Taylor polynomial, would it stop at x to the fourth?
Yes. Yeah, good question. Nathan's asking the same thing in the chat.
Oh.
So perfect. This means the largest power. So this is a definition thing. It does not mean K. Sometimes it means K, sometimes it doesn't. The K is an independent thing that we use to state our pattern. if you're doing an exam question and you are writing more than four things, you're probably misinterpreting it. So like this does not, if you went to k equals 10, you actually would be going all the way to the 85th power. So yeah, so this notation, this is great. This is something I will say tomorrow, but this is another reminder. So we now have seen today different pattern questions. So if I say T4 of x, that means everything up to x to the fourth and then stop. That's what that means. If we say the first three non-zero terms, then we mean, I never know how to say this, we mean the first three non-zero terms. For example, these would be the first three non-zero terms for that one, and it also would be the eighth Taylor polynomial. So if I just wanted to say this is the eighth Taylor polynomial of this function, that's true. It's also the first three non-zero terms. So I don't know if that helps. I'll write them side by side. The eighth Taylor polynomial of this one is 1/4 x squared plus 1/16 x to the fifth plus 1/64 x to the 8th. That's the eighth Taylor polynomial of this. It happens to also be the ninth Taylor polynomial and the 10th Taylor polynomial. Why is that? Well, because the next couple terms are 0. There is no ninth power. There is no 10th power. It's not the 11th Taylor polynomial because the 11 is something new. Yeah, thanks for being here, Jaden. But we'd also say that's the first three non-zero terms. So for the first blank non-zero terms, that's what the k is about. Yes. I mean, you could plug in a k value and actually get 0. So technically, you may have to go further. Yeah. But if you are writing like 30 different things, you've gone too far. There's definitely something wrong. Okay, so the interval of convergence question, we have to go back and think about what we plugged in, and then we'll get to part C. So interval of convergence says, well, we plugged in this to the sine series. You can see it right here. But the sine series is valid for all values, and so it doesn't matter. But separate from that, we plugged into the geometric series, and we know that that's only valid if you plug in things between -1 and 1. So this is where we have to do a little bit of work. So we need the smaller of these two intervals, which is going to be this one. So multiply everything by 4, and there's my answer. So my answer is going to be x has to be between the fourth root of this, the third root. I don't know why I said fourth root. And that's our answer. So the interval of convergence is really about what did we plug in and what do we plug it into. We good on that part? Ooh, then we get to play the exponent game. So let's do one. The original question was about this part, but I think there was value in that other piece. And it makes sense we have more. I mean, if we had had another day in class, some of this would be cleared up, but it's good we're doing this now, getting a few of these out of the way. And we'll do more tomorrow. You'll all just have a leg up. I really wanted to do this review Thursday, but Thursday is booked all day. Unless we did the review at 11 p.m. Maybe that would have been popular. All right, let's do this last one. Do we want to see this one? Yes, lovely. So this is asking about the pattern. So at some point, I'm going to have to glance back up here at the patterns. But let's just sort of recap what we're even looking for here. So this does require we have this somewhere handy. You'll notice I didn't even put them together because the question didn't ask that. The question asked me, just give me the first few terms. But we are going to need those patterns in just a moment. Okay, so we'll keep those handy. So if you missed the beginning of this, the first question we did today was this. So the moment we see this, we think, well, if we had done this the long, long, terrible way, which would really have been impossible for us to do, we would have taken 2024 derivatives divided by 2024 factorial. Please don't put that in your calculator. It will explode. I don't think it'll explode, but it won't be able to handle it. And then there would have been an x to the 2024. The question is asking what this is, but in order to figure out what that is, we're going to figure out what happens when we get to the exponent 2024. So the next time you see a question like this, we immediately go, when will the exponent be 2024? And if we can get there, I'd like to know what is in front of it. And then we're doing this funny little thing where we're saying these two have to be the same. In fact, I can lay out the entire problem. I can tell you what my final answer will be. My final answer will be 2024 factorial times whatever is in this orange box. So the real question is, what is in that orange box? That's the question we need to answer. So now we switch gears to using our pattern from earlier. When is the exponent? So the way you read this is, I want to know when the exponent in my Taylor series is 2024. So there's yet another type of pattern question. Okay, so let's go look at it and ask ourselves. And what's hard here is there's two, so that adds a degree of difficulty. There's two possible ways this could happen. This could be 2024. Maybe it happens in the second one, or it could be the first one. I'm hoping that something happens here. We have two patterns, but we need only the one approaching 2024 faster. Actually, we need either one. It could be both of them because technically if you went all the way out in this one, and let's say it's not going to be this, but 5 times 2024, and then you went way out in this one and it was 7x to the 2024, then the number in front of x to the 2024 would actually be 12. So we actually need to find the two numbers in front of each one and add them together. Oh boy. I think there's a little bit of saving grace here because if you subtract 5, you get 2019. And if you divide by 8, you get a fraction. This is not a whole number. So it's not going to happen in this one. The exponents here are all whole numbers. K is always a whole number. So 2024 does not happen up here. This one's going to go 5 and then 13. What was the pattern? 5 and then 13 and then 21. I think it was up 8 each time. It's going to bypass 2024. So this one does not have x to the 2024. I was hoping that would happen. It's just to save us some work. This one must get hit. This is 2022. And then I could talk about this a long time. This is divisible by 3. Did you know that? Do you know how to check if something's divisible by 3? We all know how to check if something is divisible by 2, but I find not that many people know how to check if something's divisible by 3. Add them up. Yay! You win, Lily. Add up the digits. 2 plus 0 plus 2 plus 2 is 6. 6 is divisible by 3, so it's divisible by 3. All right, Jacob, the practical answer to divide by 3. I wanted my I have a whole video on divisibility tricks, but divisibility by 3 is nice. You add up the digits. But now I am going to divide. So what do we get? 7, 21, 12, Yay, long division. So I got 874. Terrible. Okay, so we get K is 874. Isn't it 674? Yes. I was checking if you were listening. I wrote 18 right here. Holy cow. 674. Okay, so we have K is 674. That was really the challenge of the problem. Now that we have the number, we just plug it in. And so what's in the orange box? It's whatever this is when you plug in K equals 674. So it's going to be 1 over 4 to the K plus 1. So 675. This is 1 over 4 to the 675. And the solutions in the archive are probably going to put the fraction together. Kind of a goofy question. But yeah, if you want to be somewhere in here, I have divisibility tricks. Yeah, there you go. All right. Are we good on that one? I think we've hit some good Taylor series stuff. Wait, so you didn't use the first pattern because it's not a whole number? Yes, it would have bypassed it. Um, so yeah, it has to be a whole number. K has to be a whole number in the sigma notation. Good question. Centroid. Yes, yes, yes. If it was a whole number, you would have had to include both of them and add them together. Darn it. So this was Taylor series. Oh, what was in the box? After what's in the box? The final answer is this. That's what this equals. It's because these two things are the same. That's really the principle at play here. Yeah, that you had to multiply by this. Yep, yep. Okay, let's flip back here. So we did more Taylor series. We didn't get to this yet, but we want to find a center of mass. Did someone find a center of mass yet? Let's click on an exam. I'm just clicking on an older one. Fall 2022. Did I already go through this one? I did go through parts of that one. Okay. Further back, winter 2019. Line. Find a vector function that parameterizes that intersection. Hey, there's a circle there. There's more than one answer here, but I would do x minus 2 is 3 cosine. This wasn't the question you were asking. And this would be 3 sine. And then y would be 10 times whatever the sine is squared. That's not the question. Let's keep going, keep going, keep going. Center of mass. Okay, this was tangent plane. We know that one. Critical points. We know that one. A volume question. Darn it. Didn't hit it. Fall 2018. Find and classify the critical points. Take the partial derivatives. Draw the region, reverse the order. Here we go. Maybe this isn't what you were after, though. Let D be the region described above. The region described above. Oh, I better not do that one because it builds off the previous part. Man, does anybody find a center of mass? Well, it's a race to find a center of mass question. I know there are plenty in here. I have just clicked on the wrong things. There's one in spring 2024. Well, that would have been a good one. Let's see. Okay. So this one is saying, let's erase because I didn't actually do it. Mostly I would think of a center of mass question as it's got a computational question. This one did have a little bit of interpretation, which it said the density is proportional to the distance to the y-axis. So back when I did this in lecture, we talked about, sorry, when I posted briefly on this, we talked about what that means. So the distance from the y-axis is x. They're telling you this is the density. Now, if we were going to ask you a question, I'm kind of more partial to just outright giving you the density. So let's just for a moment say, if we have the density function, let's pretend it's this, which it is, and then they give you a region. If you want the center of mass, you have a few jobs to do. You basically have 3 integrals to compute. But however you compute them, you're going to just describe the region. So maybe we'll use, this is mostly a chance to describe the region. Let's draw it again. So it says you have this point 0, 0. You have this point 0, 2. And you have this point 1, 2. So the main thing I would be doing in such a problem is drawing this region. And then describing it. And you have 3 ways to describe it. You can do it in terms of x, you can do it in terms of y, or you can do it in polar. But please don't do this one in polar, because this doesn't have to do with a circle. So in terms of x or in terms of y. So the fact that it's a center of mass question does not change this. So the things we need to compute are the double integral over the region of the density, whatever it is. In this case, this is what it is, times x. We also need to do the double integral over the region of the density times y. And we need to do the double integral over the region of the density. And when we are done, maybe I'll put it up here. X bar is going to be whatever the first integral is divided by whatever the third one is. Y bar is going to be the second one divided by whatever the third one is. In this problem, I don't see any natural symmetry, so I think we're unfortunately going to have to compute all 3 of them. But we would just go now. So your main job here is to mow the yard, describe the bounds. So either you're going to go from there to there, or you're going to go from here to here. Both are acceptable. And I really don't know which one's going to lead to an easier computation. If you do it in terms of y, you would say for all the y's from 0 to 2, x is between whatever the right and left formulas are. If you do it in terms of x, you would say for all the x's from 0 to 1, y is between the bottom and the top. So that's really the skill in these problems. So let's say in the chat, let's say, what is the equation for the bottom? How would I label this? Y equals what? And I haven't actually given the equation for that side yet, so you're gonna have to figure out what it is. Ooh, my head's getting lower. 2x, yep. This is this line that goes through 0, 0, and 1, 2. It goes to the origin, and it has slope 2, so it's 2x. So 2x is the bottom. The top is 2. That would be correct. If you did it in terms of left and right, you would need to label these 2 things. X equals something. Sorry, I should have labeled this. Y equals 2. And x equals something. The left is x equals 0. The right is y over 2. So those are our two ways to describe that. The rest of the problem is computation. So I think I like the second one better because it has two zeros. Let's use the second one. So I'm going to do 0 to 2, 0 to y over 2, and this is going to be kx squared dx dy. You can factor the k out. Integrating with respect to x is going to become x cubed from 0 to y over 2. And that's going to be k over 3. Let's factor out the 3. 0 to 2, y to the third over 2 to the third. And so that's k over 24, because I think that's an 8. And then it's going to be 1/4 y to the fourth from 0 to 2. And that's going to be 2 to the fourth, 16 over 4. Oh, I think it simplifies quite a bit. So it's going to be k over 24 times 4, which is k over 6. Okay, so this is k over 6. Then we compute the next one. That's why I said this one's kind of painful because it's got so many things to compute. K, xy, dx, dy. And we'll go from 0 to 2, factor out the y, 1/2 x squared from 0 to y over 2 dy. Plug this in. So k over 2, 0 to 2, y times y squared over 4. So I get k over 8 y cubed. So it's 1/4 y to the fourth from 0 to 4. So it's 4. I think it's k over 2. It's k over 2. Sorry, I didn't show that. K over 8 times 16 over 4, which is 4, which is k over 2. One more. So then you would have the integral from 0 to 2, the integral from 0 to y over 2 of x dx dy. So we'd have k, the integral from 0 to 2, 1/2 x squared, evaluated from 0 to y over 2 dy. Yeah. Let me play this game for a second. So we have k over 8, 1/3 y to the third from 0 to 2. Ooh, the 8's cancel, so that's k over 3. So I'm getting this as k over 3. And I definitely could have made a mistake. I didn't check anything carefully. So we're going to get 1/6 over 1/3, also known as 1/2. And we're going to get 1/2 over 1/3, also known as 1.5. What I do like about these questions is you're doing a long computation. It's easy to make a mistake, but at the end, you can check if your point is reasonable. So you can have a little bit of confidence that maybe you did all right. That doesn't prove you did it right, but it would tell you something went really wrong. Is that okay? So those really become the place on the test where we're testing your computation. I would say that's as big as it's going to get. The bounds themselves could be polar, it could be something else. So mostly we use this as a chance to test your double integral skills. The relationship between the unit tangent, principal unit normal, and binormal. We definitely could talk about that a little bit. I probably can only do one or two more things here. Let me look and see how we did. Did we scratch the center of mass itch correctly? Other general things? I'm going to say just a little bit about. So the one thing about the TNB frame pulled from, you pulled that from, oh, that's actually from the book, but it's probably from my notes, which I stole from the book, that picture. But I since have made better visuals. Oops, I did not mean to open this. I don't think you can see what I'm doing, so that's fine. The connection, the TNB frame idea was to help us. In fact, what I'm going to do is this. This is part of why I like this gallery, is because I can grab some things that are sort of essential to what I do here. So here's a 2D version. And you can see those two red vectors. One of the red vectors is the unit tangent. It's pointing the direction the object is going. And one of them is the principal unit normal, which is pointing directly inward. Can I label these? I don't know if I set this up to nicely label. I need to be able to, I think I can do it. Yeah. So this vector is N, if I could catch it, and this is T. Couldn't catch it. There. Oh, this is bad to draw with this. No. Um, the binormal is the cross product of those two. Since we're in 2D, it's not showing the binormal, but the binormal would be pointing towards us as we watch that thing. The other two vectors, the blue vector is velocity. Yeah. The black vector is acceleration. And I like the TNB frame because I feel like they help me better understand acceleration. For example, when the object is going up, it's slowing down. So the black vector is behind the principal unit normal, and then it's in the same direction, and then it's in front. So I feel like that's where the TNB frame helps me. The derivative of the unit tangent does point straight inward. So that's that story. So this is this projectile thing. Okay, I think I showed that earlier in the term. Darn it, how do I get rid of the annotation there? Clear drawings. And then here I have, close this. Let's go back, leave. Here's the 3D version. I also have the osculating circle. Let me see if I can get rid of that. It's back when I was really enamored with adding these things. So here is this object being thrown with some wind. I believe that blue vector must be the acceleration. And so if I wanted to study the acceleration, I might want to have the TNB frame. Let me get rid of this. That's what those are. The binormal is this orange one. Zoom in a little bit. The principal unit normal is the one that's pointing inward, and the unit tangent is pointing forward. They're really interesting, but we just don't do very much with them in this course. So there you go. There's the TNB frame. The T vector points the way we're going. The N points in the direction we're turning, and the B points out. Yeah, thank you. Somebody's asking about that log question. I have a response to that. What do I need to do? This. So one thing you can definitely do, if I didn't answer your question, is search here. I don't know if I just type log, if it'll come up. But you could search by particular question. There was one that had a little bit of solving. I bet I can find it here. Let's put this. We'll click through a few. So these I've replied to. There it is. So there was a moment in this where the solving was involved, and somebody asked about this on the discussion board. So I have a post where I review that, but really you can watch, and then I remind how to use logs. I forgot that was there. I made this during Christmas time to review how to do logs, but I made it like one of those Yule log videos. So stupid. Um, and then I actually do the problem in here. So in terms, if we're worried about solving, yeah, it would be a small thing. So if you had forgotten how to solve with logs, I think you would have lost a point here. We do expect that sort of algebra to be something we can do, but it wouldn't be the main piece. All right, I think I better go. But I appreciate you all being here. That's very helpful for me to have all these questions so that we can go into this tomorrow. Eventually tonight we'll answer a few more of these things. And I'll start class tomorrow doing a few of the Taylor series type questions that came up today, and then we'll switch to review. And then Friday will be a free-for-all review. Lovely. Here we go. All right, I'm going to close it out. Thank you, everybody. If I can figure out how to do that. End meeting for all. Show meeting. End meeting.